Hello everyone, I am Diptarka Chakraborty. I am now going to present our recent work on clustering permutations. This is a joint work with Debarati and Robert Krauthgamer. Let me start with the problems that we have considered in this paper. So we have studied the classical metric K-median problem, which is a well-studied problem and which has been studied for both for general metric as well as for many special metric like Euclidean, Hamming, Edith, Jaccard, and so on. So in this paper, the metric that we have considered is the Ulam metric, which is a special variant of the Edith metric. And also we have considered the streaming model in this paper. So essentially, if the input points arrive in an insertion only stream, so then in how much small space we can solve this K-median problem under Ulam metric that we have studied. So let me now briefly motivate you about the problem. So, and for the motivation purpose, I will start with k equals to 1. So that is just the median problem. And a slightly general variant of the Ulam metric, which is the Edith metric. Okay. So the median problem under Edith metric is also referred to as the median string problem. So let me now define the problem with respect to this k equals to 1, that is median problem with under Edith distance. So in this problem, we are given a set of strings x1, x2 up to xn. And the objective is to find a string y from the ambient space such that it minimizes the median objective value. So what is the median objective value? It is the sum of distances to all the input points. And here, as I mentioned, the distance we considered is the Edith distance. So one thing I want to emphasize here that the string that we want to find is not necessarily from the input set S. And that's why sometimes this version of the median problem is also referred to as the continuous median. But throughout this talk, I will just use the term median to refer to this problem. So suppose y star be a string that minimizes this median objective function, then we call y to be a median. So how can we now find this median string? Because this median string problem is a very important problem from the practical perspective, because there are several applications starting from, say, computational biology, DNA storage system, some speech recognition, classification, and so on. So, but unfortunately, this problem is NP-hard. And if we want to find an exact solution, then the current best known algorithm, which is via dynamic programming, it takes time 2 to the n, d to the n, where n is the number of input strings, where each of the input string is of length at most d. And it is also known that we cannot do much better assuming strong exponential time hypothesis. So now the one question is, can we do better with approximation? Well, so what is approximate median? So just to make sure that we all are in the same page, let me define it formally. So suppose opt denotes the optimum objective value. So that means the objective value obtained by this y star, which is a median string. Now we call a string y bar a C approximate median if and only if the objective value attained by y bar is at most C times opt. So the main question here is, can we get a constant factor approximation in polytime? So we can easily get 2 approximations. So why? Because if you recall in the median problem, I say that we want to find a string from the ambient space, which is not necessarily from the in. Now, if we just concentrate on input and output the one input string, which attains the minimum objective value. So then, just by using simple triangle inequality, we can show that that will achieve 2 approximation. And here there is nothing specific about edit distance. So this argument holds for any metric. So now for edit distance, can we do something better? For example, can we get a p-test? Or like, can we just break this two factor? So like, can we achieve something like 1.99 approximation? So unfortunately, so far, we don't know anything. So now, since we have no idea how to get something better than 2 approximation for edit median, so one natural question is, can we do something for some special variant? And the special variant that we consider is like when the inputs are permutations. So suppose the input strings are permutations instead of arbitrary strings. So now we can define the distance between two permutations in a very similar way the edit distance is defined. So how do we define the distance between two permutations? So it is defined as minimum number of character moves. So character moves means, so from one permutation, we take a character and move it to some other position. Okay. So for example, so suppose here are two permutations x1 and x2. Now to convert x1 into x2, this is how we will do. So let's first take this character 8 and move it here. And then take the character 2 and move it here. Now you can see just by after moving these two characters in this fashion, we transform this permutation x1 to x2. And you can check later that for this example, there is no lesser number of character moves that can transform x1 to x2. So that's why the distance between x1 and x2, we will say it 2. And this is how we get the Ulam distance. So the distance that we defined just now is the Ulam distance. And as I mentioned that this is a special variant of edit distance. Why? Because if you recall, what is the edit distance? So edit distance between two strings are minimum number of character insertion, deletion, or substitution. So now, in this particular case, what you can see that each of these character move operations, you can think of it as a character deletion. So basically, once I start moving something, so I first delete that character and then insert it to some other place. Okay. So alternatively, one can also think of this distance as D minus LCS, where D is the length of the permutation and LCS, by LCS, I actually mean is the length of the LCS between these two permutations. And these are equivalent definition. But throughout this talk, I will actually never use this D minus LCS, this definition. Okay. So now, so just a few slides ago, I mentioned that we don't know anything better for edit median. So let's try to consider a special variant. But is it really a special case? So the question here is that, is Ulam median is really a special case of edit median? So actually it is not. Why? Because since now we are considering the set of permutations, now our objective is to also find a permutation that minimizes the median objective function. So now that put an extra restriction on the output median. So previously for edit median, it could be any arbitrary strings, but now that is no longer be the case. Now it has to be a permutation. So now the question is, why should we study Ulam median? Well, first of all, although it is really not a special case of edit median, but it captures some of the inherent difficulties of the edit median problem. So maybe just by solving Ulam median, or like by providing some good approximation algorithm, maybe we will have enough intuition to come up with some better algorithm for edit median problem, or like some of the techniques that we will design to get good approximation for this Ulam median, we can lift it to edit median problem. So, and secondly, so it is not just a special variant of edit median problem. So actually, this is itself is an important problem. Why? Because permutations can be viewed as ranking, and Ulam distance is an interesting dissimilarity measure. Okay, and this median for ranking is one can think it of as some aggregation of several rankings. So how? So let me now explain with an example. So suppose there are 6 candidates. They apply for some job, and maybe there are 2 open positions. So we form a hiring committee, and there are several members in the committee. And now each of these members, just by taking some interview or looking into the profiles of these candidates, they come up with some preference order. So for example, so here the committee member 1 prefer 1, and then second preference in the preference order, the 6th candidate comes in the 2nd position, 5th candidate comes in the 3rd position, and so on. On the other hand, say committee member 2 rank 2nd candidate in his 1st preference, and then 1 in the 2nd preference, 5 in the 3rd preference, and so on. So now each of these committee member come up with his or her own ranking order. So now the question is, how do we proceed with this hiring decision? Because these ranking orders are could be actually potentially conflicting, and we should not disobey any of them their preference order. So that's why our objective is to somehow come up with an aggregate rank, which using which we can proceed with this hiring decision. And also it should somehow capture each of these committee members' preference order. And one of this aggregation function that we consider is that minimizes the sum of distances, which you can see that it is exactly the median problem, but now the inputs are just permutations or rankings. So just for this example, so suppose this is my aggregated rank. Now you can see that for each of this input, that is like whatever be the preference order by these committee members, if you look into the 1st member's order, so just by moving this character 6, we get this aggregate rank. For the member 2 preference order, if I just move this character 2, then we get this aggregate rank, and so on. And you can see that between each of these committee members' preferred ordering and this aggregate ranking, the distance is 1. And as a result, if you can see that the sum of distances is 4. And you can later check that for this example, you cannot achieve anything better. So rather, like you cannot come up with any aggregate rank that achieves the sum of distances strictly less than 4. So now if we want to minimize the sum of distances, this is an aggregate rank, optimal aggregate rank. And this rank aggregation problem has several applications in social choice theory, sports, database, statistics, internet, collaborative filtering, spam detection, and so on. So I have already mentioned that Ulam distance is one of the interesting dissimilarity measures between rankings, but there are other dissimilarity measures as well that people have considered. So some of the other popular measures include Kendall-Tau or Kemeny, Spearman-Foot rule, and others. So just to remark that this Kendall-Tau actually counts the number of inversions. I mean, why I just put this as a remark, because perhaps the Kendall-Tau is the most popular measure. And also in the next slide, I will now compare our results with the rank aggregation problem under Kendall-Tau. So let's now focus on this one median problem for rankings. That is rank aggregation problem with respect to two different metric. One is perhaps the most popular one, which is the Kendall tau and the Ulam. So for Kendall tau, we already know of a betas. On the other hand, we know that this problem is NP hard, even for 4 inputs. But for 3 inputs, we don't know whether it is NP hard or P. Now, for Ulam distance, we don't know whether it is NP hard or not, even for arbitrary many inputs. On the other hand, from the upper bound side, we also don't know much. For a long time, actually just the 2 approximation was the best known. And only in the last year, in SOTA 2021, we got a 2 minus epsilon approximation algorithm. And just a small remark that for 3 inputs for Ulam distance, this problem is in P. So now let me focus on the results we got in our work for this 1 median problem. So in the beginning, I mentioned that in this paper or in this work, we get results for the K median problem under Ulam distance. So let me now explain the result with this special case when K equals to 1. So we first show a polytime algorithm that achieves 1.99 approximation. So now you may wonder that just in the last slide, I mentioned that previously there was a 2 minus epsilon algorithm. So then how our algorithm is different, or how our result is different from that. So let me now put some comparison with this previous work. So first of all, the approximation factor now improved. Previously it was 2 minus epsilon. Now it is, and that epsilon was something like 2 to the minus 40. But now it is some decent constant. It is 1.999. Okay. And then secondly, the analysis is now much more simpler than the previous one. And third, which is perhaps the most important one, is that now our algorithm, so for this 1 median problem, can be extended for K median problem for arbitrary values of K. And even with outliers. So I'm not going to define this problem with outliers, but you are welcome to look into our paper. And the fourth point that I want to emphasize is that our algorithm for 1 median as well as its extension to K median problem can be implemented in the streaming setup with small space. How much small space, that I will comment on at the end of the talk. Okay. So now let me tell you what new we have proved, or rather how we prove our new result. So the new approach that we have taken here is the following. So we essentially prove this nice fact that given any number of permutations, either there is an input permutation which is close to an unknown median. And as a result, just by triangle inequality, we can see that this input permutation will achieve good approximation, say 1.99 approximation. And if that doesn't hold, then we show that there must exist an input permutation around which there is a large cluster. So what do I mean by large cluster? So I don't want to go into the technical details here, but just in an informal way. So by large cluster, I mean that around this input permutation, there is a large mass of this objective value. And for the other points, so this particular input permutation will not perform 2 ORs in approximation. So like for whatever be the points around this input permutation, this particular input permutation will act as a good approximate median for them. And for the rest of the inputs, it will not achieve 2 ORs approximation. And as a result, when you combine everything, like combine all the inputs and compute the objective value with respect to this particular input permutation, it will attain still a good approximation, like 1.99. And then the third point is that if none of this first two happens, so then there must exist only 5 input permutations, so like 5 good input permutations from which we can reconstruct an approximate median. So I want to emphasize this third point here, because you should observe that just by looking into 5 input permutation, or like performing some algorithm over this 5 input permutation, we get a approximate median of the whole input set. And once we have this theorem, which I am not going to prove in this talk, so you are again welcome to read our paper for this proof. But now let me explain, how we can use this theorem to come up with a good algorithm. So once we have this theorem, actually the algorithm is pretty straightforward. So this is what we will do. So just try all possible 5 tuples from the input set and run that reconstruction procedure. And how many possible 5 tuples we have? Since there are n input points, there are n choose 5. And now we add all this output to our candidate median set. So there will be roughly n to the 5 outputs, and also all the inputs I will add. And then finally, from this candidate median set, whatever be the candidate that attains the minimum objective value, output that. And since there are only roughly n to the 5 order n to the 5 candidates, we can perform all the things naively in polytime, as long as this reconstruction procedure runs in polytime. Okay, so now assuming that reconstruction procedure runs in polytime, so now we are in a good shape. We get a polytime algorithm. And now just because of this theorem that we have described in the previous slide, so one of this candidate from this candidate median set attains 1.99 approximation. So now next question is, how can we extend this to k-median problem? So what is k-median problem? So again, we are given a set of permutations, and now our objective is to find a subset of at most k permutations. And again, this subset, a set of k permutation, okay, y, and again this set y need not be a subset of this input set, okay? And now we want to minimize the following objective function. So for each of the input points, I will compute its distance to the nearest neighbor in this set y and take the sum. So this is just an extension of the one median problem. So instead of outputting just one input, one permutation, now I am outputting at most k permutations. And why our algorithm can be extended for this k-median problem? This is just because of the following reason. So if I now consider any arbitrary k-median clustering, so now one can observe that our candidate median set still contains 1.99 approximate median for each of this cluster, because our construction was completely oblivious to this clustering. And as a result, if I just output the best k tuple, we achieve 1.99 approximation. Now, if you run this thing naively, we will end up with consuming n to the order k running time. But with the use of clever sampling, we can reduce the running time to k log n to the order k. So now the last thing that we want to comment on is, what about streaming? So in this streaming setup, all my input points are arrived in an insertion only stream. And now for the one median problem, if I just sample log n inputs uniformly at random, then we can show that just by performing our algorithm, we can get the same approximation. And only one point to note here is that how do we find the best candidate? Because if we cannot store all the inputs, how can we compute the objective function? Well, for that, we can use some of the known construction, of course. And for the K-median version, in the streaming setup, we can do the similar stuff. So we can just build a proper course set. But now, instead of uniform sampling, we have to do slightly clever sampling. And then essentially just using K-square polylog n sample, we can perform our algorithm and attain the same approximation. So now let me conclude my talk with mentioning some of the open problems. So first important open problem that I want to highlight is that can we get a p-test for Ulam median? So either for Ulam K median or like just for Ulam median when K equals to 1. And then secondly, can we show that Ulam median is actually NP hard? Which I mentioned before that for Kendall tau that is the case, but we don't know anything for under Ulam distance. So can we show a similar result? And thirdly, can we lift some of our technique to this more general edit median or for a Ulam center problem? Okay, so now thank you. And let me now conclude my talk, and I'll be looking forward to meeting you in the conference.